Good morning, everyone, and thank you for joining us here in Houston, Texas at the NASA Johnson Space Center. I am Gary Jordan. Thanks for joining us here for our Media Day here at the Johnson Space Center. I hope everybody's been having a good time. It's really good to see a crowd of this size out of the Johnson Space Center. You'll notice that most of the day today has been, and most of your experience has been looking at Artemis as a whole and the future that the Artemis I mission will be bringing us very soon. At this point in our Media Day, we're going to bring together a panel of experts to discuss the Artemis I mission in more detail. We'll discuss the mission operations, the recovery operations, the Orion capsule, the European service module, and astronaut training that's preparing for Artemis II and beyond. So joining us to provide remarks and answer questions, we have here at the Johnson Space Center, Rick LaBrode, lead Artemis I flight director, Judd Frieling, Artemis I Ascent and Entry flight director, Debbie Korth, Orion Program Deputy Manager, and Reid Wiseman, Chief Astronaut. Joining us remotely from NASA's Kennedy Space Center in Florida, we have Melissa Jones, Artemis I Recovery Director, and joining us from the European Space Agency in the Netherlands, Philippe Deloo, Orion European Service Module Program Manager. Thank you all for being here. We'll first start with a short presentation from each of our briefers before opening it up for questions. We'll be taking questions on our phone bridge as well as here in the room. For those here in the room, please raise your hand nice and high so we can see you and run a microphone over to you and then ask your question once you actually have the microphone. For those on the phone, please press *1 to enter into our queue so we can get to you and you can ask your question. Now we'll start with our experts here at the Johnson Space Center. I'll first hand it over to Rick and Judd. Go ahead, gentlemen.
All right, thank you, Gary. And as Gary said, my name is Rick LaBrode. I'm the lead flight director for the Artemis I mission. And before Judd and I start with our mission overview, I just want to take a moment and thank you all for coming out today. Our teams have been working extremely hard for a very, very long time to get to this point, and this is very special. We're extremely excited, and we want to make sure that the public feels our excitement and hears our story. And we realize that we rely completely on you all to do that. So thank you so much for coming out today and showing interest in our mission. So we'll go ahead and pick up with an overview of the mission. I'm going to hand over to Judd to start the first part.
All right, good morning, everybody. Let's see, Artemis I, our first planned launch attempt will be August 29th with planned splashdown of October the 10th. Charlie Blackwell-Thompson and her team at the Launch Control Center at Kennedy Space Center will hand over the vehicle. Once they launch that vehicle and unleash the 8.8 million pounds of thrust, we'll start our journey. If we could have the graphic there. Once we start the liftoff and the vehicle clears the tower, we'll start a roll program that will bring the Orion capsule to a heads-down position, much like we did in shuttle. About a minute into the flight, we'll experience our maximum dynamic pressure, and so the four core stage engines will throttle down for that period. Throttle back up, and then about 2 minutes into the flight, the solid rocket booster motor engines will expend their fuel, and they will detach from the core stage, splash down in the Pacific. The Atlantic. We continue on to another about 3.5 minutes or so. The service module panels will jettison along with the launch abort system, and those will expose the solar rays on the service module and the capsule of Orion, the command module. Continuing on further throughout the flight until about 8.5 minutes where we will have main engine cutoff. And after main engine cutoff, we'll separate the core stage from the combined Orion and upper stage or interim control upper stage, interim propulsion control upper stage. That will continue on then to about 18 minutes MET, mission elapsed time. We'll deploy the Orion solar arrays to provide power to the batteries. That'll take about 12 minutes to deploy. We'll continue on to our first burn that is going to be performed by the upper stage. That's called the perigee raise maneuver. The core stage puts us in an orbit that's 16 nautical miles by 975 nautical mile orbit. So if we did nothing at that point to correct the perigee side or the small side, that 16 nautical mile orbit, the whole capsule would come back to the Earth, just like the core stage is going to do in the Pacific. We'll perform that perigee raise maneuver to 100 nautical miles at approximately 51 minutes into the mission. The whole time, the upper stage will be in control of the stack. In the interim, it'll be doing several maneuvers to get to a solar-friendly attitude for the Orion spacecraft. It'll also do some roll maneuvers to make sure that the whole vehicle is thermally conditioned. Pressing on forward, once we have attained a safe orbit with the perigee raise maneuver, we'll continue on, and our final maneuver by the upper stage will be the translunar injection orbit maneuver by the upper stage. That will be approximately an hour and 30 minutes into the flight. That'll be about an 18-minute burn, and will send us all the way to the moon, approximately a 250,000 miles away. And once we completed the translunar injection maneuver and separate the upper stage from the Orion spacecraft, then my team will hand over to Rick, and he'll start the majority of the mission there. So Rick, you want to talk about that?
All right. Then if we could go to the next chart, please. So there's really no time to catch our breath. We really hit the ground running. As you'll see on this first chart, after we separate from the upper stage, it actually does a disposal burn, which sends it on a trajectory to the moon, a heliocentric, which is it'll swing around the moon and then head towards the sun. And on its way to the moon, it actually will be deploying a handful of 10 CubeSats, their secondary payloads. We have no interaction with those secondary payloads. The only thing we're concerned with is their initial trajectories, where they're being deployed, so we can do an assessment on a potential recontact. Everything should go nominal, there's no concern, but we need to make sure that their trajectory is what we expect. So with that, I want to get away from this chart. Let's go to the next chart. We'll take off the ICPS piece of it. So. I'm going to talk through a lot of this. You know, it's 42 days, and I'm going to try and do it in just a handful of minutes. So, by all means, there'll be plenty of time to ask questions after we're all finished here. I said we hit that first day. We hit the ground running. One of the first things we're going to do is we have to do a test of our guidance and navigation control system. There's a set of gains that are used, and the way they fire the thrusters in our normal attitude control. And we need to make sure those gains are set such that we don't damage our solar arrays. So we're going to be doing that right after. That's one of the first things we do once we separate. And then we're also on that first day going to do the first of a handful of outboard trajectory correction burns. And this very first one, we're going to actually be checking out the orbital maneuvering system. It's the big engine that we'll be using. We want to check that out. Because that's the big burn. That's the engine we're going to use when we do the big burn on the outbound powered flyby as we go by the moon, and I'll talk about that a little bit shortly. But that first burn, like I said, it's a checkout. It also will get us moving ahead of the upper stage and those satellites. So we should get to the moon somewhere on the order of 2.5 hours before the satellites and the upper stage do. So that's why there's no really concern of recontact. So on our way to the moon, like I said, we'll be doing a series of these outbound trajectory corrections. They're very small, or at least they're designed to be small. If we end up having dispersions because a burn didn't go as planned, then we'll make it up in a subsequent burn. I think we have 4 of those on the way to the moon, and those all set us up for what I said is the outbound powered flyby. That's the big burn that will actually move Orion, then it'll send it up to the distant retrograde orbit. So when we do that burn and we go by the moon, we're going to be about 60 miles off the surface of the moon. It's going to be spectacular. We'll be holding our breath, but yeah. And to that note, when that burn actually executes, Orion will be on the other side of the moon, and we won't have time with it. So we'll be praying and holding our breath, but confident that all will go well. So after that burn, like I said, it sends us up to the distant retrograde orbit. A couple days after that burn, we will do what we call an insertion burn. It's a distant retrograde orbit insertion. We'll also use that big engine, the OMS engine, to enter the distant retrograde orbit. And then once we're in the distant retrograde orbit, we're going to spend a little over 2 weeks there. You've heard us talk about long class missions and short class missions. The only difference in those two types of missions are the length of stay in the distant retrograde orbit. For a short class mission, we just do a half a lap, and then we head back towards the moon. For the long class, we do a full lap and a half, and it's a little over 2 weeks. While we're in the distant retrograde orbit, we'll be doing what we call orbit maintenance burns. They're small burns just to keep our orbit in sync. We'll do that over the course of the next 2 weeks, and then we'll do what we call a distant retrograde departure burn. It's another large burn that uses the OMS engine, and that'll send us back to the moon. And on our way back, now we're doing what we call return trajectory corrections, RTCs, and we'll do a series of those all the way back to Earth. So we have a couple of those. Then that sets us up for the return power flyby. That is our most critical burn of the mission. If something happens with that one and we don't execute it, then it's a loss of the Orion capsule. We have to do that one. But we plan accordingly. We have down mode capabilities, and we can talk about that if you have questions. But so we do the RPF, which actually sets up the entry interface. That's the area where when we enter the atmosphere several days later, and sets up our splashdown off the coast of California. On the return trip back to the Earth, we do a series of these correction burns that I talked about, and it's all to make sure that we hit that entry interface target as designed. And you know, I've gone through the mission very quickly, just so you know. On those days where we're coasting the moon, we're doing a lot of activities. We're doing a lot of developmental flight test objectives to just basically test out the onboard systems. We're doing a public affairs outreach event every day where we maybe maneuver, do a selfie of Orion with the moon in the background or the Earth in the background. On some days we're going to try and catch the Earth rise. That's a spectacular image. There's a couple milestones throughout the mission where we actually enter the sphere of influence of the lunar, where the lunar gravity really starts taking effect. That's a milestone that we'll try to capture in a public affairs imagery. When we get to the point where we're actually the furthest away that any human-rated spacecraft's ever been, further than any of the Apollo vehicles went, we want to capture that in a public affairs event. So we'll be busy the whole mission. I went over it really quick, but yeah. So once we get back to Earth, we do RTC 6, which sets up that entry interface, and then I hand it back to Judd to take you through the rest of the mission.
Thanks, Rick. Yeah, as Rick mentioned, that return power flyby maneuver is essentially our deorbit burn. That's way back at the moon. It's about a week before we enter the Earth's atmosphere. So about 20 minutes before we enter the Earth's atmosphere, the entry interface, we'll separate. You can go to the slide there that we have. Next slide. We'll separate the command module from the service module. And once we perform that, we'll get into the proper orientation. We'll put the command module in the proper orientation for entry. We'll do a little bit of a set burn after the command module and service module separation. That's to shallow out the angle that the command module is entering. So it's just provides a little bit more separation from the service module, which is going to dispose in the Pacific Ocean. We'll start our entry interface, and we're actually doing what's called a skip entry profile. So we'll hit entry interface at 400,000 feet, and then we'll immediately start to control the lift vector of the capsule such that we dip a little bit in the atmosphere, and then we come back up out of the atmosphere a bit, and then come back in. So we'll have two blackout periods of COM due to the plasma heating of the capsule. Once we get out of that second period, we will continue our journey towards our splashdown site, which is going to be in San Diego, off the coast of San Diego. We have the forward bay cover jettison. Actually, I think the next slide is a little better picture to show you the sequence. Once we get a little further down into the atmosphere, about 5,000 feet are forward bay cover jettisons that brings out the drogue chutes, and those drogue chutes deploy around 24,000 feet, followed by the mains at about 6,800 feet and between 6,800 and 5,600 feet, and then we'll continue on down to 1,500 feet, where the Orion capsule will do a landing reorientation maneuver such that it'll roll the capsule so that we're going to hit the waves of the ocean at the proper angle. Let's see, and once we splash down, we'll leave the vehicle powered for about 2 hours, and we're going to do some testing there, thermal testing to make sure that we have adequate cooling for astronauts when we do eventually have them on board and are waiting to be picked up by the recovery crew. Then after that 2-hour period, we will power down the vehicle and we'll hand over the vehicle to Melissa Jones and her team, the recovery team that's there on a Navy boat. So with that, Gary, I'll hand it back to you.
Thank you, Judd. Thank you, Rick. A 42-day mission in 15 minutes. That was fantastic. Thanks for the detailed mission overview. Let's go over to Debbie Korth to talk about the Orion spacecraft.
Okay. Good morning, and thank you guys for being here. It's great to see this room full of people and see all the excitement about this mission. Very exciting time for NASA. Very exciting time for Orion. Been working on this for a long time and really looking forward to where we're going to go on this mission just 24 days from now, headed back to the moon. So it's just amazing. So let's go to the next animation. We've got some graphic here to kind of explain the pieces of the Orion the Orion vehicle. It's made up of 3 main elements. Is there an animation that we can show?
Yeah, let's see.
There we go. Okay, thank you.
Yeah.
So made up of 3 main modules, the crew module, the launch abort system, and the service module. So you've heard the crew module also referred to as the command module. That's that silver capsule there in the center. The silver surfaces you see are our back shells. It's made of about 1,300 silica tiles, very similar to what we flew on the bottom of the shuttle during the shuttle days. And it's covered in some paint and some Ciox tape and aluminum tape to help with thermal protection. So that's kind of what you see there on the outside. On the bottom of the crew module, you'll see the heat shield that we've talked about being one of our primary test objectives on this flight. It's 16.5 feet in diameter, so it's the biggest heat shield we've ever built. It ablates some material away as we re-enter. The crew module also has its own small propulsion system. It's got several reaction control system jets that perform those type of maneuvers that Rick alluded to on the re-entry when we have to orient to the right orientation before landing. Parachutes, 11 total parachutes that you just saw pictures of that deploy in a very time sequence to slow the vehicle down from about 350 miles per hour down to less than 20 when we hit the water, which Reid will be happy that we're at that speed hitting the water. Pyrotechnics throughout the vehicle. We talk about jettisoning things like the launch abort system or the service module when we're done with it. We use these pyrotechnic devices that help make those vehicle separations. And then when you go inside the cabin, you've got your environmental control and life support systems, so everything that controls pressure, temperature, and humidity inside the volume. That crew module is designed to hold 4 crew members for 21 days, and so obviously on Artemis I we're flying uncrewed. This is our test flight, so expect to learn a whole lot about how all these systems work. Inside the vehicle also there's avionics systems, our guidance, navigation, and control, communication systems, which are a lot different than the GPS you probably used your map to get here today. It doesn't work outside of the distances we're going, so we're using a deep space network kind of system for our communications. And then several payloads that we're flying on this flight, several of which are in the crew seat location. So we won't be flying crew, we'll be flying some mannequins and some torsos that are simulated human tissue and organs that are looking at radiation protection, radiation environment, the acceleration of the vehicle, and how that affects the human body, because our goal is for the crewed flight on Artemis II. For future crewed flights, won't be on this mission, but we'll be adding in a waste management system, a galley, and exercise equipment, all for crew health and comfort and safety during the mission. So we can go to the next slide. So this is the crew module and the service module located in our factory at the ONC. This is before we install the launch abort system. Artemis I, as you know, we're testing all these systems and capabilities, and this will be the kind of configuration of the vehicle that will be available mostly during the mission that we're talking. One of the main objectives you've heard is about the heat shield, and so the heat shield is the vehicle comes back at about 25,000 miles per hour, and we end up at temperatures of about 5,000 degrees Fahrenheit, which is about half the temperature of the surface of the sun. So we're talking about very high temperatures we're trying to protect for. We have a block design for this heat shield. It's made up of these Abcoat blocks that are adhered to a skin and a skeleton, and we'll be testing that as one of the main objectives. But of course, when you look at the spacecraft, we talked about some of the other objectives as well. You can see the solar arrays here folded up against the vehicle. We'll be doing what's called the modal survey of those solar arrays once they're deployed, and looking at how they respond to different jet firings, engine firings, to make sure they can handle the vibrations and the loads that they'll see throughout the mission profile. Checking out all of our guidance and navigation and control, and then obviously the parachute systems as we come back in. Okay, next slide. So next picture is the vehicle as it came into the vehicle, the vertical assembly building there at KSC. So it looks a lot different now. We've got the fairings around the crew module and service module, and we've got the launch abort system mounted on top. So the launch abort system, didn't talk about that previously. It's designed to pull the crew capsule away in case there is an emergency on either the launch pad or during the ascent phase. So it's made up of 3 solid rocket motors. The first is the abort motor, and that's what actually pulls the crew member away. Very powerful. It goes from 0 to 400 miles per hour in 2 seconds. So we're talking very quick, really trying to outrun an SLS that might be having an issue during launch. At the top of the last system is the attitude control motor, and that's what's used once it is separated from the hazardous event. It steers the crew module away and allows it to get to a safe location. And then finally the jettison motor, which would jettison the launch abort system from the crew module. So on Artemis I, that jettison motor is the only active motor. We don't plan on using the other functions. This is a non-crew flight, so we didn't put those motors on the vehicle. But the jettison motor is the one that works every flight. So it's either, eventually you take the last off, whether you're in a nominal flight or in an emergency situation. Okay, I think we can, let's see. We can go to the next slide. So this is a picture of us rolling out to the pad for one of the wet dress rehearsals. Before we got to this point, every component, every system, every module on this spacecraft has been thoroughly tested. We've done over 48 engine tests between the aux engines and the main engine that we talked about to make sure we have a robust propulsion system. That parachute system that we showed, 25 different drop tests that we did, chunking capsules and lawn darts out the back of military aircraft, making sure that we can handle every parameter, things like chutes out or different wind conditions, wave conditions, looking at all of that through that test program. Literally thousands of hours of avionics and software testing in the laboratories here at JSC and at Denver, where our Lockheed Martin prime contractor is located. And then we took the entire spacecraft to a thermal vacuum chamber up at Glenn Research Center, the Armstrong Test Facility, and it spent over 47 days in that chamber, just really wringing it out, testing every aspect of the temperatures that we'll see, the vacuum, the pressures, acoustics, and so really have spent a lot of time testing this at the component and module level. If you've been following Artemis for a while, you also know we did 3 flight tests. We've done 2 complete flight tests of our launch abort system. So one was a pad abort 1, which was looking at performance from a pad escape, and one was the ascent abort 2, which was looking at it during that very dynamic phase of the ascent. And then finally we had our exploration flight test 1 that happened a few years ago that tested out most of the crew module systems, and obviously we've added things today, and then we've also added our service module. Okay, I think we can go to the next slide. So here we are on the pad. This is the last picture we took before we rolled back into the VAB, and I just love this photo. It gives me chills to see this moon in the background, our destination sort of calling to us. Just a huge amount of collaboration, testing, and energy and effort that's gone into putting this together. We had over, I'd say 3,000 to 4,000 suppliers in every state of the United States. So really just a huge effort across our country. Also have a very strong partnership with our Europeans on the European service module. So didn't talk a lot about the service module. Our Philippe Deloo, who's the manager of the service module program, is online, so I'll be handing over to him to let him talk through the details there. But we're rolling out on the 18th and just looking forward to this flight and everything that we'll be learning from it. So Philippe, if you'd like to talk through the service module, that would be great. Thanks.
Yes, thank you, Debbie. So we also at the European Space Agency are very excited about this upcoming mission, which will be, let's see, coming with, after 10 years we started this program. Sorry, I have a blank. Yes. So I would have loved to be in Johnson in person in order to take this media event, but I'm taking it here from the research center at the European Space Agency here in Holland, in the mission room that our engineer will use here to support the mission. This is in addition to the team that will be in Kennedy. Can I see the next slide, please? So as Debbie said, the service module is one part of the Orion vehicle, and we're extremely proud at ESA that NASA has trusted us and our industry to provide critical function to the Orion vehicle. Those critical functions are the propulsion, the thermal control system, the power generation, and the storage of consumable for the crew. So the service module has 33 engines, one main engine, which is an engine recovered from the shuttle. This is the orbital maneuvering system of the shuttle. And then 8 auxiliary engines. Those 8 auxiliary engines are also a backup in case of anomaly of the main engine. And 24 engines for the attitude control and attitude correction during the mission. The propulsion system also includes propellant tanks, who can store 8.6 tons of propellant, and the pressurization system. Now moving to the thermal control system, this is a fluid loop where a pump is pumping fluid and distributing this fluid within the ESM. One of the main functions of this fluid loop is to reject the heat from the service module, avionics equipment, but also from the crew module in order to keep a comfortable environment for the crew. The next function is the power generation. This is, of course, provided by the solar panels. Those solar panels provide 11 kilowatts of power. It provides basically in an hour more than you need in order to supply the need of a home for over a day. So in addition to the solar panel, there is a power conditioning system in order to condition the power and distribute it to the service module, but also to the crew module. And finally, the last system is the crew consumable. In the future version of the service module for the Artemis II Mission Plus, this will provide water, oxygen, and nitrogen. For this Artemis I mission, we will only load nitrogen in the tank. There will be no oxygen tank, and the water tank will be empty. Next slide. So this is another picture than the one showed by Debbie. It's a bit earlier in the integration phase and Kennedy, so it was not already mounted on the spacecraft adapter, and the solar array were not there. So it was just right after the mating of the crew module to the service module. So this is Artemis I, or the Orion for Artemis I. The service module for that vehicle was delivered in 2018. The service module for Artemis II has also been delivered and is now in Kennedy under integration. It's been delivered last year in 2021. Right now, the third service module is being built in Bremen and will be delivered to Kennedy in 2023. And then the service module for ESM 4 to 9 will follow with a yearly cadence from there on. Next slide. So this is a picture that has been already presented, and here I will emphasize a bit more on what will happen for the service module. I will not insist on the propulsion. I think the propulsion has already been very well described by my predecessor. I presented 4 functions of the service module. Those 4 functions will be verified once on orbit. For example, for the thermal system, we will check out that everything is functioning nominally. We will also verify that our prediction of the thermal behavior of the vehicle is as expected, or whether there are things that we did not predict properly and will need to adapt or correct to validate our prediction. Same thing for the power system. One feature which is unusual on this spacecraft is that the solar array has 2 gimbal axes. So not only you can track the sun by rotating the solar array on their axis, which is usually what other spacecraft do, but also you can cant the solar array forward and backwards. And this is needed for 2 reasons. One reason is during the big burns, because structurally the solar arrays would not be able to withstand the loads if they are at 90 degrees of the service module. But second, it allows to have a better tracking of the sun when the vehicle needs to have a specific attitude, for instance, when the vehicle will be approaching the gateway. Also, as I told you, we will have nitrogen on board, and the reason why we will have nitrogen on board is because there is a major verification to be made, is that in case of a accidental depress of the crew module for any reason, we want to check that we are able to repress the vehicle with nitrogen that is stored on the service module. And yes, once we've completed the mission, the service module will separate and unfortunately will burn in re-entry in the atmosphere and will fall in small pieces of dust in the South Pacific Ocean. And that concludes my presentation, my short presentation of the service module, the European service module. And now I will hand over to Gary.
Thank you very much, Philippe, and to Debbie as well for giving us insight into the Orion spacecraft and the European service module. So we've taken a look at the mission profile, we've taken a look at the spacecraft. Let's now go over to Melissa Jones over at the Kennedy Space Center to take a look at recovery operations. Melissa.
Thank you. Hello, everyone. It's my pleasure today to be here to talk to you about the recovery operations that we're going to do in order to recover this Artemis I Orion capsule. For the past several years, the team based here at Kennedy Space Center have been working with the U.S. Navy to refine, refine, and practice our recovery operations to get the capsule back when it lands for Artemis I. Just last fall, we completed our final test called Underway Recovery Test 9 aboard the USS Martha, and that certified us to do these recovery operations. These recovery tests allow us to experience life aboard a Navy vessel for 6 to 8 days as we are practicing with a full-size Orion mock-up. And we practice over and over again what will happen on splash day to refine how we work with the capsule and integrate with the Navy. We have a decades-long partnership NASA does with the Navy, as I'm sure you know from our time with Apollo, recovering human spaceflight missions, and this Artemis program will just build on that experience that we have with them. So speaking of that, so NASA chose the Navy's LPD landing platform dock class ship, specifically because of the well deck that it has, the helicopter pad, its onboard medical facilities, and the communication capabilities. You can see a picture of it on the screen. This class of ship also provides us the communication assets that we need to communicate back with the flight control team at JSC. You heard Judd talk about it earlier. So on recovery day, we will be in communication with his team, listening for burns as they happen and information that will allow us to know what are we going to get when the capsule lands from a health and status perspective. During the mission, the capsule will travel about 25,000 miles an hour before slowing to 300 miles an hour after entering the Earth's atmosphere. And when the parachutes deploy, we're expecting it to slow to about 20 miles an hour before it glides into the Pacific, or we'll go get it. And that landing location is approximately 50 to 60 nautical miles off the coast of California. During the final hours of the mission, what we do to prepare while the capsule is getting ready to come back through entry is we deploy some helicopters off of the flight deck of the ship. We talked about that, and some divers. If we can pull up the first slide, we'll have a picture of the divers interacting with the capsule. But basically, those folks need to be in the open water and the air because we're trying to get as much data collected as we can upon entry. So we want to see the parachutes, we want to take imagery, we need temperatures, how is the TPS performing, and so it's very important that we already are deployed so that we can get that information as quickly as possible. And then the deployed team of divers is pictured on your screen. The very first task that they will have is trying to get to the jettison hardware that was mentioned before it sinks. There's a forward bay cover that comes off of the top of the capsule. Judd talked about that earlier. And 3 main parachutes. Those are the top priorities we have for getting back as quickly as possible that hardware. Now, of course, if we can get back drogue chutes or any of the other parachutes, we will absolutely try to do that. But those are our priorities. And while that's happening, there will be some tests happening on the Orion vehicle that were mentioned for cooling and other things. So we let that capsule sit powered up for a while we're focusing on jettison hardware. And so you can see once we're ready to recover the capsule, the divers will approach the capsule, which is in the picture that you're looking at. They will attach something called a pony collar, which is that colorful black and yellow and red and orange collar around it. And that allows us to attach lines to the capsule so that we can tow the capsule into the back of the ship, into what's called the well deck. So if you want to go to the next picture. You can see that all of the lines are attached, and we now have a ship that the picture is actually being taken from a rib, which is a rigid hull inflatable boat where the Navy is holding the capsule from the back, and there are lines being attached to the front from the ship, and then we will tow that capsule into the well deck where we will hold it steady while the Navy drains the well deck. If you want to go to the final picture, you can see a copy of what it looks like inside, a picture of what it looks like inside. And you can see there's a lot of water in the well deck. We flood it. The Navy floods it. They drop the stern gate, pump a bunch of water in there. That allows us to pull the capsule in. And then in the front corner of the screen, you can see the yellow there. That's underwater, but that's the Orion Recovery Cradle Assembly. And we will hold the capsule steady with those lines while the Navy pumps all the water out of the well deck and softly land the capsule in that cradle. This whole timeline will be probably 4 to 5 hours long, which is a lot longer than it will be for crew. But this objective for this first mission is data collection and engineering data that will allow us to fly crew on Artemis II. And so we are very careful with all the TPS, the heat shield, all of the things that the Orion program needs to do to look at this capsule to say, yes, we think we can fly crew on the next one. I think that's probably enough data for now. I'm sure we'll get into some more details during the question and answer period. I'm going to hand it back over to Houston at this time.
All right. Thank you very much, Melissa. Now you're seeing the Artemis I mission from end to end. It's testing the Orion spacecraft that will eventually carry humans to and from the moon, and those humans are training as we speak. So to talk about the humans that will make that journey, let's go over to Reid Wiseman.
Hey, thanks, Gary. Thanks, everybody. This is unbelievably exciting to look at the Artemis I mission in so much detail. Obviously, we don't have crew on the first flight, but we have 42 active astronauts here at Houston, 10 astronaut candidates, and we'll be beating down the door for Artemis II and beyond. When we think about Artemis, we focus a lot on the moon, but I just want everybody in the room and everybody watching to remember our sights are not set on the moon. Our sights are set clearly on Mars. And everything that you're thinking about today, everything that we're going to do on Artemis I leads to Artemis II, which leads to Artemis III when we hope to have humans on the surface of the moon. But Artemis III is leading to the rest of the Artemis program. The first woman, the first person of color on the surface of the moon, and then the first humans tracking out to Mars and putting our footsteps in building science laboratories and inhabiting another planet. To me, it's just the most awe-inspiring moment that we have had here at NASA, and I love working here right now. It's an honor to get to do so. So what are our 42 active and 10 astronaut candidates doing right now to prepare for all of this? I have just a few very quick slides, far less detail than my NASA counterparts here and my European friends there, Philippe. But in order to land on the moon, in order to land on Mars, we're going to come down pretty much vertically. Whether it's SpaceX Option A, building their human lander for the moon that we will fly, or our other contractors that are coming online to take subsequent missions, we're almost certainly going to come down vertically. So we're spending a little time right now with the Army just to get familiar with landing vertically, landing in snow. What does it look like to be whited out like you would be on the surface of Mars or on the surface of the moon? And just a few hours in helicopters, but it is amazing how much you learn, how quickly you learn. And we are doing that not so that we're good at landing vertically, but so we understand the new and different risks when you don't have a runway that you're landing on. And you learn a lot very quickly. Next slide. We have been working off the planet for quite a while on this little tiny thing called the International Space Station. There's a great picture of Raja, who just came home on SpaceX Crew 3. He was the commander of that vehicle. Our crew is up there right now. Crew 4 with Chell and his crew, and they're conducting science day and night, 24/7, 365 days a year, and we've been doing this since the year 2000. And every day that I personally spent on the space station, I looked at it as walking on Mars. That is why we're up there. We're trying to make life better on Earth, and we're trying to expand humanity into our solar system. Next slide. This makes me jealous. One of my classmates, Kate Rubins, is somewhere in that photo. Two-time flyer to the space station, a microbiologist, and we have her out in a European training session just a few months ago called Pangea, where we're going out and looking at all lunar geology, how we would sample rocks, how we would get lunar samples, retain them, catalog them for the scientists on Earth. What we need to think about is a totally different way of thinking in a geologic timescale, and just thinking the way a geologist would think on the surface of the moon and onward to Mars. So we're doing that training. We also train a lot in Iceland. It is a very good analog to the lunar surface. Next slide. Some of you this afternoon will go over to our virtual reality laboratory, and virtual reality is just paying enormous dividends right now. So we expect the next human landing on the moon to be at the South Pole. And if you've ever looked out at the moon at night, the South Pole has got a very weird sun angle, very weird light that hits it. There's permanently shaded regions. And we have developed, hopefully you'll see it this afternoon, we've developed in the virtual reality world what it actually looks like with the exact sun angle that we'll be landing at. And it is crazy weird. The bottom half of you can be in absolute blackness, and the top half of you can be in blinding sunlight. The way shadows are projected across the lunar surface, it just changes literally everything. So in this virtual reality world, we can go in there for 10 minutes, and you can answer 1,000 questions. You can stop 200 meetings with 10 minutes of VR goggles. And so it's really a great facility. I think you'll like it. All right, next slide. We also, over in Building 5 here at the Johnson Space Center, we have the Orion crew trainer. There you have Stephanie, Johnny, and Randy Bresnick, who have been heavily involved in the development of Orion the last few years. What it'll feel like to fly, and that trainer is being outfitted right now and will be ready later this year to start our crew training. Next slide. And the final slide in this, I think some of you were out this morning at our Neutral Buoyancy Laboratory about 10 minutes north of the Johnson Space Center. Very large pool where we have been training for International Space Station spacewalks for 2 decades, and now we're taking a portion of that pool and looking at what it would look like to be on the moon. To spend 6 hours in a lunar class spacesuit doing research on the bottom of a pool, and it's an amazingly fantastic facility to be underwater, to spend that much time thinking about how it will be to be on the moon. So we'll be using that as we move forward. And that's the end of my PowerPoint pitch. The question that everyone will ask is, when are we assigning a crew to Artemis II? And we hope that'll be later this year. Thank you.
Very good. All right, thanks to all of our briefers for the very detailed overview of the Artemis I mission and what we are doing for the future to build upon Artemis and going to the moon and to Mars. So we're extending our time for the briefings to give us about 45 minutes for questions. So we'll spend some time taking some questions here in the room, and then of course on our phone bridge. So a review of how we're going to take the questions. Raise your hand nice and high so we can see you, and then we're going to run a microphone over to you, and then you can ask your question with the microphone. We'll start over on this side, and then please state, once you have the microphone, state your name, your affiliation, and to whom you'd like to direct your question. We have folks from all over, so just make sure you state to who you'd like to direct your question. If you're on the phone bridge, please press *1 to submit your name into the queue, and then once your name is called, you can direct a question to anyone here on the panel. If you find that your question has already been answered, you can withdraw it at any time by pressing *2. So with that, let's start here in the room on this side. Please go ahead. Yeah, and we can state your name, affiliation, and to whom you'd like to direct your question.
Chris Gephardt with NSF. I believe they're for Judd. In terms of Ascent, with the launch abort system not having its abort motors installed, what abort options are available for Orion, and when do they become available in the Ascent profile? And on the flip side of that, for landing, when you're coming into San Diego, what if the weather isn't good at the landing site on October 10th? What are your options to target a different one? What are the backup landing options for the 10th?
It's a great question, Chris. Our abort options become available after the last jettisons, about that 3.5 minute mark. Our first abort mode that we have available to us is untargeted splash. So that would be where we'd separate and splash down somewhere in the Atlantic Ocean. We also have an overlap between that untargeted abort splash mode and then an abort once around option. That's about 7.5 minutes or so into the flight where we have that overlap. And the abort once around would take the capsule and put us off the coast of California in the Pacific. Additionally, we have, once the solar arrays are deployed, after about that 18 plus 12 minute mark, we have available to us, should something go wrong with the upper stage, we have the option to abort to orbit. So we'll do an orbit. Obviously, we wouldn't be going to the moon in that fact. As far as your question on entry, what options do we have for abort landing for weather? Once we do our deorbit burn back at RPF, return power flyby, our trajectory along the Earth's surface is fixed. So the only things that we can do to modulate is to land a little longer than we intended or land shorter than we intended. So uprange or downrange. And so we have several sites within 1,200 nautical miles of San Diego that we'll be looking at to make sure we can, and we're 90% confident that we'll be able to find one that will fit all the conditions that we need to splash down. Melissa didn't mention this, but 3 days out before splashdown, her recovery team is going to be halfway between that 1,200 nautical mile and San Diego. And so once we have a better idea what the weather's going to be like, we'll either send the recovery forces inland, or if the weather's bad inland, then they'll proceed outland.
Okay, yeah.
Hi, is this working now? All right. Hi, my name is John Moan. I'm a correspondent for Newsy. And again, apologies for the redundancy here. Once we get all the data from this unmanned mission, what's a refined timeline for when human beings are going to be going back to the moon?
You want to answer that?
Yeah,
Yeah, so after Artemis I, the next step will be Artemis II, which is planned for 2024. So that'll be our crewed mission. We'll take all the data from this flight, The Artemis II, you saw pictures of the European service module for Artemis II has already been delivered. The crew module and the launch abort systems are already well on their way of being fabricated down at Kennedy as well. So we talked mostly about Artemis I today, but those vehicles are already rapidly being built. Plan to hand those over to our ground support friends in mid-2024 and launch by the end of 24 for crew. As far as Artemis III, targets in 2025, so we're trying to do annual missions after that. It's kind of outside the scope of this briefing because there's a lot of other components that have to feed into that. But in terms of the Orion vehicle and the launch system, those are both targeted to be ready by then.
Mark Carreau with Aviation Week in Space Technology, and my question is for Rick LaBrode. How will this mission inform mission control and the team to prepare for the crewed flights, either 2 and 3? I guess what I'm saying is, what will you guys be focused on to make sure that you've got the bases covered for when you have a crew?
That's a good question. Excuse me. So right now, all the performance data that we have of the vehicles really is test data that Debbie talked about. We supported all those tests, but it's all either test data or models, theory. And this mission is going to inform all the models. We're going to see how the vehicles are going to really perform in the environment that we're asking it to perform in. And so all that information is going to be knowledge that we're going to gain. We're going to be updating all of our procedures and our documentation to make it more accurate as to how that vehicle is going to operate. And that's just going to make us smarter controllers for when it is time to put the crew on the vehicle.
Irene Klotz, also with Aviation Week, probably for Judd. After the perigee raise maneuver, how long before the TLI burn might there be to have Orion stay in Earth orbit if there's some issue? And also, what's the battery life on Orion before the solar arrays need to be deployed?
Great questions, Irene. Let's see. So first question on perigee raise maneuver, how long can Orion stay on board orbit if there was if there was a problem? So if there's a problem with the upper stage, Orion still has the OMS engine available to it, so we can circularize, we can raise its perigee if we need to on its own, so we can perform an orbital insertion. Although in that case, we're likely not going to the moon. Does that answer your question?
No, if there's the upper
Can you pass the mic down? Thank you.
If the upper stage is available, but some other issue comes up where you're not burning according to your nominal timeline, is there an option to delay the TLI burn?
That's a great. Okay, I understand your question now. No, there's no option. So the upper stage is pretty much a fire and forget vehicle. If it doesn't perform the perigee raise maneuver, or if it doesn't perform the TLI maneuver, Orion does not have the commodities to get to the moon by itself. So it has to be put on that TLI burn by the upper stage, and it has to be at the times that we prescribed. Your second question about the batteries, how long do the Orion batteries last before the solar arrays? They can last about 45 to 50 minutes, or a little bit in that hour time range, just enough to get to the abort once around, should that be needed.
Hi, Robert Perlman with Collect Space. One for Rick and one for Reid. Rick, realizing there's no crew on board, how is the flight team going to be referring to the vehicle when it's in orbit over the loops? Does it have a call sign, or is it Orion, Artemis I? And for Reid, are there members of the astronaut corps who are assigned to specific technical roles for Artemis I, supporting either as a Cape Crusader or on reentry or in mission control?
Mine's easy. It is Orion. We'll refer to it as Orion.
Mine is more complicated. Many of these people you know well. Stan Love will be working in mission control. He'll be following along as if we had a capsule communicator on console. So Stan will be looking from mission control perspective. Randy Brezick has been following Orion on our technical side with the Orion program for the last few years, so he'll be looking at the technical aspects of the mission. Joe Acaba is our VIT chief, so he will be down at Kennedy Space Center looking at all of our processes leading up to the pad, and then also on return. And then I will also be at Kennedy for launch, looking at where will we be putting family, where will we be in launch control the day that crew is on board the vehicle, and I'll be there with our flight ops director, Norm Knight, as we do that. That's the small scale, but also understanding that this Artemis I mission gets everybody fired up. So there is a large press element. So you will see astronauts all over. With the administrator, we'll be doing a lot of interviews, especially I know this afternoon, a lot of folks will be touring you around as you're going through Johnson Space Center. So we'll be all over the place, but for the technical roles, those are really the folks we have assigned.
One quick follow-up. So I said Orion, which that's what we'll call it, but we do have the crew module and the service module, and a lot of the systems are like there's a prop system on both modules. So we would then refer to it at the crew module or service module level.
Thank you. Tarek Malik with Space.com. I believe I have one for Reid and maybe one for Melissa. Reid, with some systems like the waste management, et cetera, not flying on Orion, I'm really curious what the experience you're looking for the astronaut corps to get from the sensors that are going to be on board the mannequins, et cetera, in the spacecraft. How germane and how accurate can you get a picture of what that experience is going to be like? And for Melissa, on recovery, with an extended retrieval time for the testing, what's the target recovery for an actual crew that you're going to want to aim for? Thanks.
From the crew on board standpoint, I got to be honest, the thing I'm most looking for is how does this integrated system work? How does the core stage vehicle dynamics work on Ascent? I know that will all be good. How does the ablative block heat shield architecture work on reentry? That is something we'll be watching. For the ride inside, we've been working on this vehicle for years. We've been doing egress training. We've been looking at the waste facility, the exercise facilities for years. That is not what we're looking to get out of Artemis I. This is a robust vehicle. It's built to go to deep space. It's going to be ready for crew when we're ready to fly there on Artemis II for sure.
Yeah, I might add, on Artemis I, we are flying, like I said, some payloads that will help inform our models and make sure that the design that we have predicted is actually realized during the flight. So, the kinds of environments we're worried about, radiation, vibration, accelerations, all those things we're measuring in the vehicle. The heat shield has hundreds of sensors embedded in this abcoat block. So we'll be collecting, actual temperatures at actual locations, different depths, different locations. Same thing with the landing loads. We've got sensors that are picking that up. So really, I think, in terms of crew protection and crew occupancy, it's really about validating the design so that we're ready. These other systems like waste management, galleys, exercise, we do have a lot of those capabilities to test on the ground. We have crew over all the time testing out those facilities. If you're going to Building 9 later today, you'll see the mock-up, and there's all of those capabilities in there. As well as the vehicle that we're building up now for Artemis II already has the waste management system has been installed for a year. So we and in terms of that one specifically, that same waste management system has been flown to space station. So Reid mentioned about a lot of the stuff we do on space station informing our data. We use that as a test bed all the time to prove out the things like fluid dynamics you really want to test in zero gravity, right? So the waste management system's on board today.
We did have another second question for Melissa. Let's go over to Melissa. Okay.
Hi, that was a great question. So our requirements for getting crew to medbay is 2 hours. I will tell you that our estimates think that we can beat that pretty significantly. We think we're looking at about 80 minutes. I will tell you that, however, the capsule that you saw in the picture that we showed you does not have an interior, and the trainer that we're using to refine those egress procedures with the DoD and timing is almost finished. It's actually going through final stages of verification and validation. So as soon as Artemis I is over, the very first underway test we will embark on with the Navy will have that new capsule that has a hatch and seats in it, and we'll start refining how quickly we can get to the capsule, open the hatch, get the crew out, and get them to medbay on the ship. So estimate is 80 minutes at this time, but we think that we can beat that and refine those procedures.
Excellent. Let's go back in the room.
Gina Sinceri, ABC News. I think this is for you, Rick. If you launch at 8:33 a.m., it's a 42-day mission. If your launch slips in that window, how does the mission duration change and why?
Okay. Actually, the mission duration doesn't change at all. It'll force our team to do a lot of replanning, but for the most part, the mission is identical. That's the beautiful thing about allowing for a 2-hour launch window. It gives us flexibility for the launch teams to successfully launch, and we can still execute the same mission. The primary burns may slide on the order of minutes, but pretty much the mission will be the exact same.
And I'll add on to that. So the reason that it's the same duration is every launch day we're targeting the same point in space for TLI, translunar injection, and so when we move through that window, we're just changing the angle at which the rocket is approaching that TLI, and actually that TLI is moving westwardly, throughout that window. So we're changing the angle at which we're approaching.
And at risk of getting way out over my skis, so we're gonna roll here. We have 3 launch steps, right? We've got the 29th, I think the 2nd and the 5th, but I think this is a really important point. We're flying this vehicle as a test flight. We do not know everything. We've modeled everything. We've evaluated everything. We've tested everything we can test on the ground. But it's a whole different ballgame when you roll to the pad and you go to get off of that pad. So there's a very solid chance we go for the 29th, and we don't make the 29th. And there's a chance we don't make the 2nd or the 5th. And in that case, then we're going to roll back to the VAB. We're going to reset a few systems, and we're going to go back out. That next set of 3 launch attempts, we do go to the shorter class 22, I think, day mission. So just keep in mind, there's a lot of unknowns still out there. So
yeah. So just make sure it's clear. So the 29th, the 2nd, and the 5th are all long class. They're going to all be 40-plus day missions. But if we roll back and then we go into the next launch period, then we start off. It's generally the first part of the launch window, which is several weeks, is a short class, and then we transition to a long class.
Go ahead.
Hi, okay. Bill Harwood, CBS News. I just want to follow up on those last ones. We've all been told the 29th, 2nd, and 5th. Charlie Blackwell-Thompson said last week, or earlier this week, if you roll out on the 18th, she said you get 2 attempts. Explain what's going on there. I don't understand the flight termination system, battery install. When does that clock, that 20-day clock, if it is a 20-day clock, when does the 20-day clock start ticking? And if you roll out on the 18th, what's your last opportunity to fly? In other words, do you really get all 3 of those opportunities or not? And a second question I'm squeezing in. I'm not standing in my driveway looking out at the moon. What are you guys showing me with your finger? What is the orientation of that orbit as I'm looking at the moon? Because Apollo, it's going around the moon, it's an eclipse, around the moon, eclipse. What is Orion doing in that distance? In order, as I look at the moon from Earth, try to visualize that as an eclipse. Sorry for too long.
That's good. That's a great question. I'll take the first one.
If the briefers can reiterate the question, we actually didn't capture that for TV, okay. So just a quick reiteration and then answer it. Thank you.
The first question that Bill had was, what is the actual constraint on the flight termination system, and where does the 20 days that Charlie Blackwell-Thompson talked about come from? And where does the clock start? So the clock starts during the processing in the VAB. That window starts when they install the FTS batteries, they charge them up. That's when the certification period or the starts at 20 days. So I believe, and I'm not exactly sure the day that they're planning to do that, but that'll be around like the 16th or 17th, something like that. 20 days later, the range has told them that the batteries are only certified for 20 days, and so I think that puts you right after the 2nd, so like the 3rd or 4th, right there, not quite to the 5th. And so that's where, why she quoted 2 days attempts, right? Because the 20-day certification ends right on the edge of being able to pick up the 5th. I do know that they are in talks with the range, the Eastern Range, to try to extend that certification to a little bit longer than 20 days, hopefully to bring in a 3rd attempt, but those negotiations are still in work. As far as your second question, I don't know, Rick, you want to take that one?
Sure. Your reference from standing on Earth, watching it, is very similar to what the Apollo trajectories looked like, in that it's in the Earth-Moon plane. So as we fly by the Moon and do that outbound powered flyby, we'll be on the backside, and we'll lose comm with it, and then it just goes up, and we'll stay in that plane, and it's doing a big orbit around there. So when we do that big orbit, that first 6 days, we're going to have a loss of comm for on the order of 3 hours, because the Moon is blocking the pathway to the Earth. So it's very similar to Apollo, just a lot farther. They would go in lunar orbit, and we're going to be in that just distant retreat. Yeah, it all depends, but yes, probably.
Hi guys, Tom Costello with NBC News. Thank you for a terrific briefing. Thank you very much. I had a couple of quick follow-ups. You had mentioned that there are 2 blackout periods on reentry, and I'm blackout for comms. I'm curious why that is. Shuttle, as I understand, did not have any blackout periods. So what's changed? Is it the reentry position? Is it the speed? Why 2 blackout periods on reentry? And then the second one is, if there were to be a reason to abort on liftoff, any chance at all of aborting to the space station, or is that not possible at all?
Thanks, Tom. Good questions. As far as the blackout period, the orientation of the antennas, that all has to do with why the shuttle didn't have the blackout. Originally, early on in the shuttle program, there were blackout periods until they were able to get antennas on top of the shuttle to look up at the teeter satellites. As far as the double blackout, it's just antenna orientation, and there's lots of plasma coming around. The vehicle. I believe the Soyuz is the same has the same issue, right? There's a period of time where there's blackout due to the plasma field. As far as your second question, no, there's not. It's not a possibility to abort to the space station. It's not even anywhere near the same orbit.
Okay, so it's good. Okay, Joanna Pinkworth from Polish Public Television. The question will be for Reid. Do the astronauts from Artemis mission need some different training than other astronauts who are flying for the ISS or something like that? And how old are they?
The way I look at it is, right now we have 42 active NASA astronauts here. Artemis is an international program, and we'll be flying colleagues from around Earth on this vehicle as we move forward. Right now, every one of our astronauts is eligible for an Artemis mission. So if you get assigned to a space station mission, you go into a space station training track. If you're assigned to an Artemis mission down the road, you'll go into a very specific Artemis training track. While we're not assigned to those missions, I personally want our astronauts to be as well-rounded as possible. Even though you may not walk on the moon, studying geology in Pangaea helps you when you're on the space station looking down at our Earth, looking at the geologic processes that you get to see for 6 months or a year when you're looking down. And the thing you never get with robotic missions are these eyes and this brain. And we can think up some crazy things when we are left to be a little bit bored. It's just amazing what you get to think about on the space station for 6 months when you look down at our beautiful planet and watch it orbit the sun and see how it changes. So I say we're all the same until you get assigned a mission, and then you go into a specific training track. And for age, we have anywhere from late 20s all the way up to mid 60s. And as long as you are healthy, there is a tiny bit of medical testing on us. As long as you are healthy, then we're going to load you in a rocket and shoot you off the planet. And walk on the moon, and then onto Mars.
Good morning, Jeff Faust of Space News. Artemis 1's flying the distant retrograde orbit, which is not an orbit that you're planning to use for future Artemis missions. I wonder if you can talk about some of the benefits and trade-offs of flying DRO versus the near rectilinear halo orbit that you're going to be using for Artemis 3 and beyond. And also the difference between the short and the long class missions. Are there mission objectives that you would be able to achieve with a long class mission that you would not be able to achieve with a short class mission because of less time in the DRO?
I'll take a shot at that one. So I'm very focused on the Artemis I mission, so I don't have a lot of knowledge about the other Artemis missions. But I think the knowledge we'll gain from getting to the moon and getting back, that how we're going to build trajectories and burn plans to do that. And that's exactly what we're going to use once we get to the moon in order to get into these specific orbits around the moon. So Artemis I, albeit it's very different from as you alluded to, we'll still gain all the knowledge for how this vehicle is going to operate as far as the burn plans and targeting these special burns that put us in these different orbits once we get to the moon. For your second question regarding the difference between the short class and long class, actually we will be able to accomplish all of our mission objectives on a short class mission. They'll be closer together, but we will be able to accomplish all of them, even on a 26 to 28 day mission. The challenges we have to deal with is we have thermal constraints where we can go out of attitude to do some of these activities, but once you go out of attitude, you're limited to 3 hours, and then once you come back into attitude, you have to be tail to sun for 10 hours to get the thermal recovery before you go off and do another one. So to plan all these activities, these events, to ensure that we can meet all the objectives, it's a very tightly choreographed timeline to ensure that we meet all the thermal constraints. But we've built timelines for the short class missions, and we can meet all our objectives.
And on the distant retrograde orbit, because of the Moon-Earth gravity interaction with that orbit, we can stay in it. It's very stable. It takes very little prop to actually stay in that orbit. So that's one of the advantages of being there. We can get a very long mission, really wring out the systems. Whether it's a short class or long class, it's going to be quite a bit longer than the first crewed flight, which is targeted 10 to 12 days, something like that. So we're getting this very long orbit. We can really wring out the systems without a whole lot of prop load to stay there. It's part of it.
And then looking forward for the NRHO for Artemis II and beyond, the advantage of that orbit is that it's always facing the Earth, right? So you have something that's always facing the Earth, and it'll allow several different types of vehicle, whether it be Orion or the lander, to rendezvous with the gateway and then go to the moon surface.
Check. There you go. Dan Schaefer, Way 31 in Huntsville. This is a follow-up for Reid on the astronauts. So you've culled 40-odd astronauts now down to about 10 who want to fly on these first couple of crewed missions. How did you do that?
Oh, we have definitely not done that. So we have 42 active astronauts, and then earlier this year, some of you folks were here, we announced our latest class of astronaut candidates with 10 Americans from across our country, all walks of life, to join our Corps, and they're in their initial training right now. When they graduate in about 18 months, then they'll come into the 42 active astronauts with us. Right now, we are truly, we have not made any flight assignments. We have not necked down who is going to do what missions at this point in time. We want to watch Artemis I, and then we want to make the right smart decision when we assign 2, and then eventually 3 and beyond.
Thank you so much. Roseanne Aragon with KPRC. Thank you so much for making time for us. I have 2 questions. The first is for Reid. We know the Apollo generation is watching, and this means so much to them. What is your message to those who worked on the Apollo program and how their expertise contributed to what you're working on today?
What I would say to them is thank you. That Apollo generation landed humans on the moon at a period where I truly look back and think it was impossible. And then that technology, the very Johnson Space Center that we're sitting at right now, is a legacy of the Apollo era. But I don't think about that when I think about Apollo. When I think about Apollo, I think about every kid that watched that landing and wanted to work in mission control, that wanted to be an astronaut, that wanted to be a doctor, that wanted to be a school teacher. Like, the impact of what Apollo did was not putting Neil Armstrong and Buzz Aldrin on the moon. It was changing the way we look at STEM completely. There is nothing that motivates someone more than doing. And that is what Apollo did, and that is what Artemis is going to do. We are going out there and we are going to do this, and that way you really energize everyone.
My second question is more of a technical question. I see a lot of big mission objectives here: testing the guidance and navigation control, seeing how the orbital maneuvering system does, making sure you nail the return power flyby. What is your margin of error, especially considering some of these things have never been done to this capacity at all? What's your margin of error, and what does success look like if not all of your objectives is met?
Okay, well, the margin of error is small, but those trajectory correction maneuvers that I'm talking about, they're what are going to ensure that when we fly by the moon, we're at the right altitude and we don't run into it. And I talked about the burns. We assign a criticality to them. So a non-critical burn is one, if we didn't execute it, no harm, no foul, we can pick it up, we can make it up later. Then we have mandatory burns, where if you don't execute that burn, then you lose a mission objective. A good example would be the outbound powered flyby. So if we didn't do that, then we wouldn't be able to get up to the DRO and do the DRO mission. We'll still safely bring the Orion back, but we won't be able to accomplish all of our mission objectives. And then the last category is the critical burn. That's the return power flyby, and that's the one, if we don't execute it, then it's a loss of the vehicle. So the margin of error is small, but we have opportunity to make sure that we make all the right corrections to make sure that we target our outbound powered flyby and our return powered flyby. So confident that we'll be able to execute the trajectories as necessary as long as the vehicle performs the way it's designed, we're going to get the mission accomplished.
And I would add to that, I mean, this is a test flight. So we're also finding where the margins are, right? We're finding where the conservatism in the analysis that we've been previously done. And so in many respects, we're continuing to learn, right? And so we'll find where those margins are.
Hi, I'm Cooper Heim with Singularity and Everyday Astronaut. Apollo had Hasselblad as the camera on the moon, and I'm curious to know, does Artemis have a camera?
Actually, Artemis has a lot of cameras. Debbie probably could talk better to the internal ones, but on each of the solar array wings, we have a GoPro that's wireless, has a wireless link to the crew module, and we'll be taking imagery a lot throughout the entire mission, and we'll be transferring that imagery from the GoPro camera down to the. We have camera controllers internal to see them, and then we'll be bringing those down to the Earth. But there's internal cameras also that I don't know the make of those. Do you know?
Yeah, I don't know the make. There are several cameras inside the crew module, and actually there's a technology demonstration payload being flown called Callisto. You can read about it if you haven't already. It's a collaboration with Alexa. And actually, so you'll have a camera on board. You'll be seeing, from the vantage point of a crew member sitting in a seat. And actually, participants can interact with that. If you have Alexa at home, you can ask questions. Where's Artemis today? Where's Orion today? What's happening on the mission today? So there are various camera views, both externally. Some of that's imagery you want to capture for post-flight analysis. Did things perform the way we want, or did that solar array deploy and lock into place? So definitely, the cameras external help us during the mission if we start seeing data that looks like an anomaly. But then a whole bunch of video inside too as well for just see what's going on.
Is that the same for whenever they go down to the moon? Will that be mostly GoPro? Will that be a red? Will that?
Yeah, good question. Those are Artemis III related, so I wouldn't be able to get to the answer today. I'm sure Gary can get you some information on what's happening on those. Mm-hmm.
I might sneak a cell phone. They're pretty good cameras.
Yeah.
Thank you.
Sure.
Over here, Daniel Alfonso from The Independent. A lot of people ask questions about numbers and mathematics and specifics, and I want to talk about the human aspect. This is the very first time that we see an African-American, a woman getting into the moon. Diana Trujillo from Colombia being the flight director. Astronauts from Ecuador origin, from Salvador, from Puerto Rico. How important was for NASA to send that message out there? That this was like driving into diversity and inclusion, all of you guys. That's double.
Absolutely a priority. I mean, it's something we think about every day. And so, this mission to me, professionally, I'm very excited and proud, but I also personally, I have 3 kids, 2 of which are daughters. And so when I talk to them about, we're going to send a woman to the moon, they can't even understand but there hasn't been one. So they grow up in an environment where things are just so much more diverse and inclusive. So absolutely, to me, from a professional, but also from a very personal standpoint, I think it's a huge, huge deal that we've made this a very big focus of this mission for both women and people of color. Yeah.
Absolutely. That's our job at NASA, is to do the things that are difficult and to do the things that are right and to motivate our base, which is our youth. And right now, our country is a diverse and extremely rich country, and we want our astronaut corps to look. We want every kid in America to look at our poster and say, "Oh, I see myself in that. I grew up poor, or I grew up in this state, or I grew up with this type of family. I can do that someday." And it's really important for all of us to stand together as we go and do this. And the neatest part about getting to work at the Johnson Space Center and at NASA as a whole is the team you work with. Every day when you get to work, the stories you can tell, the flight director class that we just hired that's truly from all over our country and the world, it is an amazingly rich place to work. And it's reflected every year. It's the best government agency to work in, and there's a reason for that, because we're a bit progressive and we really love what we do.
All right, I'm going to go to the phone for a second. They've been very patient, so I just want to give them an opportunity as well. Marvin Marshall with the Nighttime News Space Report. Go ahead.
Hi, my name is Marvin Marshall from the Nighttime News Space Report. I appreciate you guys having us out here today. My question kind of banks on the camera question there. I was wondering, how much public engagement will there be to mean the live streaming from orbit? Pictures are worth 1,000 words, but that video just does so much more for us. Now, will there be like an emphasis on providing the public with live streams after the launch live stream, on orbit, that initial live stream, and like on Artemis I or even Artemis II? And thank you for taking our questions. Thank you.
Okay, I'll try to answer that if I heard it correctly, and if I didn't, you can ask again when I'm finished. But yes, throughout the mission, we will be having live stream imagery coming down, but it's in competition with all the data that we need to get down as well. We are limited on our data rates that will be transmitting information down from Orion throughout the mission. There's periods where we'll go to a high data rate, where we'll be able to do imagery and then also maintain our telemetry. But for a lot of these events, we'll also be recording the high resolution imagery, and then those would be downlinked after the event. We have a priority list of how we're going to bring files off of the Orion. So it's going to take a matter of time, because there's a lot of data that we'll be bringing down on a continuous basis. So it'll be somewhat after the event to get the real high res, but the intent also is to have some streaming imagery during these events as well.
Let's go to Melissa real quick. So she wants to add a little bit about what happens at the recovery phase for imagery. Go ahead, Melissa.
Awesome, thank you. Yeah, so we have about 17 cameras all over the ship, in helicopters, in the open water. Several of those are connected to basically a satellite system that we have on board that we will be able to stream near real-time live video back to Johnson to be sent over NASA TV. So you will be able to see recovery operations real-time.
Very good. Let's also go to the phone. Last one on the phone, Marcia Dunn, Associated Press.
Yes, hi. For Reid, I was hoping you could provide some details, please, on what special traits or skills you're looking for the first two crews. And will the first two crews come from the 18 Artemis team astronauts announced a couple years back, or not necessarily, because today you seem to be indicating that any of the 42 active astronauts could be in the running at this point for Artemis 2 and 3. Thanks so much.
You bet, Marcia. I'll start with the second half, which is the way I look at it, any one of our 42 active astronauts is eligible for an Artemis mission. We want to assemble the right team for this mission. As for what we're looking for in these first few Artemis missions, but I would say it's really what our astronaut corps is as a whole right now. First and foremost, technical expertise, the ability to dive into literally any situation, any technical need of the vehicle, to understand when things aren't going quite right and to understand when they are. That is absolutely number one. And then beyond that, it is, are you a team player? Are you engaging? Can you work with our flight directors? That is exactly what our astronaut corps is today. We pride ourselves on long duration space flight, 6 months to a year on the International Space Station. We pride ourselves on, we call it expeditionary behavior, of being a good teammate, of emptying the trash can when it's full, cleaning out the dishwasher when your parents ask you, those sorts of things. And that is really what we're looking for in those first Artemis missions. Technical expertise, team player, and that's what we want.
Very good. Let's go back in the room.
Florian Meyer with ARD, German Radio Television. Thank you for doing that. I wondered if there are, since you made it clear that Artemis I is about collecting as much data as possible, are there any moments or points throughout the mission where you're going to push the SLS, the Orion, closer to the limit than you would normally do when humans are on board?
I would say probably not to any extreme events. We have, most of our testing on the ground covers those extreme corners. So when I talk about like parachute testing, a lot of parachute testing with a drogue out or a main out, what happens when that happens? So we try and catch the corners of the boxes through our ground testing. So I think, we're looking, but we use that ground testing to build models on how the system's going to perform across all environments. So really during the mission, we're capturing the data so we say what environment did we really fly in, and then the response, in that environment, did the thermal and the pressures and the temperatures or the vibrations or whatever we're collecting, did it match the model predictions that we have based on all of our test data? So that's where I think we are. I think there probably are some operational things that we'll be a little more aggressive about because we don't have a crew, and our number one objective is to get the heat shield data, right? So there might be, let's go for TLI, which we maybe wouldn't have been the call if you had crew on board, but because that is our primary objective, absolutely, we might take a little more, I wouldn't say risk, but, a little more flexibility there, but I'll let
to elaborate on that. I think it's a good point. We established a philosophy on the planning stages of this mission that we would accept more risk. So during the LEO phase, the low Earth orbit phase, before we do that translunar injection, if Orion sustained a failure that it rendered it zero fault tolerant to being able to safely recover and retrieve the capsule, we're going to lean forward and we're going to press and we're going to execute the translunar injection just so we can achieve the number one mission objective, that getting that heat shield data. While we get that, we'll also be able to pick up most of the other ones as well. We'll be able to operate the vehicle in space. We'll be able to, Melissa and her team will be able to get on site and recover it. Because what we'll do is we'll burn the translunar injection and then we'll select an early return trajectory to bring Orion back quickly. We won't make it to the moon. We may do a lunar flyby depending on the nature of the failure, but that is so we can get that number one priority objective and then safely get the vehicle back.
And then on the SLS side, we don't have automatic aborts. So we'll have automatic aborts that for the crewed vehicle. So they're all manual aborts at this point. So we're leaning forward in that aspect for the SLS as well.
And I guess one other item, Melissa may want to jump in. After the reentry and splashdown, she mentioned that they have up to 2 hours from a requirement standpoint to get the capsule in. Obviously, I think we're going to beat that. But I think on Artemis I, we are leaving it in the water for 2 hours. We're doing a thermal soak back. We want to understand what is that thermal environment inside the capsule when we finally have crew in there on Artemis II. Did we predict correctly? Because they're going to be in suits. How long can they stay in suits and stay cooled? So in a case like that, we are pushing beyond what we expect on the mission just to collect the data again to validate the design.
Yeah, let's go ahead.
Hey, thanks. Joey Roulette with Reuters. If I remember correctly, there's going to be 2 mannequins that are female and 2 that are male on Artemis I. And I guess this is for Debbie or Reid. Is there a difference between how astronauts respond to radiation on the capsule, and if so, how, and what changes will you make to either the spacecraft environment or the spacesuit, if depending on the results?
So I think, and I'm not fully up to speed on all the payloads, but there is one full mannequin called Munikin Campos. It was a naming contest that happened several months ago. And then there's these 2 called Phantoms, which are just torsos. One's going to be wearing a radiation protection vest, and one is not, so kind of comparative. Radiation does affect women, obviously, differently than men. I don't know if there's something else from the crew standpoint you want to mention, but we're collecting the data to understand, did the protection of the vehicle provide what we expected?
So we used to have, I won't call them draconian, but maybe I said the word, some radiation limits that were definitely different for men and different for women. And we have worked very hard through our agency, and we've gotten some outstanding leadership at headquarters right now. And we have equalized all radiation limits. It does not matter whether you're a man, whether you're a woman, it is the exact same. And our end goal is, the United States of America is half men, half women. Well, space should be at least that. And so if we cannot make these spacecraft equitable and we can't fly any type of person on them, then we need to look at our systems and reevaluate. So from where we stand, there's absolutely no difference.
All right, last question.
Scott Johnson with Spaceflight Insider. I think the rollout is about 13 days away, and then hopefully we have a launch in about 24 days. Are there currently any issues being worked on the vehicle and the VAB that would affect either of those 2 dates?
I can speak from a Orion perspective. The answer is no. We are ready to go. The vehicle's powered down. I think today we're closing the hatches in a couple of days to prepare for rollout. When it gets out to the pad, the hatches are opened again for some other late load items. But from an Orion standpoint, we have some minor what they call non-conformances when we process the vehicle at Kennedy. But it's things like touching up little paint or things here. So nothing right now on our list that's holding us up. We just completed our JSC Center Director pre-FRR pre-flight readiness review yesterday and successfully passed that. So we're good to go. I can't speak for the rocket. I don't know if you guys have more.
I'm not aware of any issues on the rocket that they're working at this time.
And we'll go to Melissa to talk recovery ops.
Hey, I was just going to comment on the question. I am here at Kennedy. I do share a wall with Cliff, who is the one who's getting us ready to roll out. I could tell you that we, at this time, are not working any showstoppers. I can't give you any technical details on any of the nonconformance we have, but we're looking pretty good right now for holding both of those dates.
All right, that'll wrap up our time for questions. Thank you all for submitting your questions in to our briefers, for taking the time to do a detailed brief of the Artemis I mission. You can follow more about the mission on nasa.gov/Artemis-1. All these charts that you saw during today's briefing will be available online, so we can point you in the direction if you're interested in those. Thanks again for joining us. That'll wrap up today's briefing.
Two, one, ignition. And liftoff.
Copy, 1 Alpha.
Pushing downrange. Trajectory nominal.